Hello, everybody. Thank you to the organizing committee to let me present my work. So my name is Ozan Lacinbala, and I'm a postdoc at Institut des Sciences Moléculaires d'Orsay with Thomas Pinault. I'm going to talk about a plausible explanation for the near-infrared continuum emission via the recurrent fluorescence by a specific focus on this reflection nebula. So before presenting my work, I would like to stress the main result, which is that near-infrared continuum emission observed in several interstellar environments can be modeled by the recurrent fluorescence from KH carbon clusters containing approximately between 30 and 60 carbon atoms. And this recurrent fluorescence takes place during the radiative cooling induced by the absorption of a starlight photon. This theoretical investigation is based on a large sample of carbon clusters. And to begin, I will introduce the carbon clusters used in this work. After that, I will describe the photophysical processes and their modelization. I will finish with the simulation results, so the collective emission of carbon clusters in isolated conditions, in interstellar medium conditions. So we know that pH-like molecules are supposed to be the carriers of interstellar of aromatic infrared bands, and this is explained by the radiative emission induced by starlight photon absorption. And also we know that Buckminster Fullering and C70 molecules have been detected in interstellar environments, but we don't know the Fullering formation, which allows us to consider the presence of large carbon clusters in the interstellar medium in this environment. And if so, large carbon clusters should have the same photophysics as that of pH molecules. And the question that we address is that what should be the collective emission signature of these large carbon clusters? So firstly, large carbon clusters have already been detected in the laboratory. So for example, 30 years ago, by graphite laser ablation technique, C60 cationic and ionic species have been detected in ion mobility experiments. Also, carbon clusters, large carbon clusters, are product of incomplete combustion, and maybe they are also soot precursors in flames. And as mentioned by Shubhati Chakraborty, maybe carbon clusters are also produced in shock-induced decomposition of Buckminster Fullering. So what I did is to use carbon clusters that have been generated by our colleagues. So they generated several thousands of carbon clusters, theoretically, structures, for three sizes, C24, C42, and C60. And they investigated the vibrational and electronic structures for each of these isomers. These carbon clusters can be classified among four families according to their structural shapes: cages, flakes, pretzels, and branched. And what I did is to take 1,000 carbon clusters among each of these families of each sizes, and I simulated the collective emission induced by radiation from a star, 20,000 Kelvin black body. So the photophysical mechanism induced by starlight absorption is as follows. So a carbon cluster is electronically excited and undergoes several internal conversions up to reach the ground electronic state. So the electronic energy is converted into vibrational motion. And given that we are in isolated conditions, we also have inverse internal conversion, which allows to the molecule to be electronically excited again. And at each of these electronic states, we also have intramolecular vibrational redistribution. Besides these very fast radiationless transitions, we also have radiative transitions, which are vibrational emission, and also electronic de-excitation, which is called recurrent fluorescence in this case. This recurrent fluorescence have been have been introduced by Alain Léger more than 30 years ago, and since 10 years now, reaction fluorescence is observed in the laboratory in ion storage rings. And our question is, what is the resulting emission spectrum of carbon clusters from this photophysical mechanism? And thus the collective emission of carbon clusters of our sample. And to do that, we have to simulate the emission rates, vibrational and recurrent fluorescence rates. And to do that, the main hypothesis is that the internal energy is always statistically distributed among all vibranic states, which allows us to estimate these emission rates by statistical mechanics calculation, because the vibrational density of states is very high in this kind of species. For example, for the recurrent fluorescence rate, the model is based on the same have already been presented by Christine. For example, for the recurrent fluorescence rate at E internal energy, the recurrent fluorescence rate from the N electronic state N to the ground electronic state is calculated by the product of two quantities, the electronic fluorescence and the probability to occupy this electronic state. And this is calculated in the microcanonical framework. And for each carbon clusters, we computed the recurrent fluorescence from the first 50 excited electronic states. In the same way, we can calculate the vibrational emissions, but in the vibrational harmonic approximation. And once we know all the emission rates, we can simulate the radiative cooling by a kinetic Monte Carlo method and deduce the collective emission spectrum. So we simulated the radiative cooling for each of these isomers and deduced the collective emission spectrum. So here we have a comparison of the recurrent fluorescence rate and vibrational emission rates for two molecules, this C60K isomer and the well-known benzene molecule. And we can see that the recurrent fluorescence and the vibrational emission are in competition during the radiative cooling for this molecule, these carbon clusters. This is also the case for the other carbon clusters, but the recurrent fluorescence is completely negligible for the benzene, because this is explained by the very low excited electronic state of the carbon clusters, which allow to the excited electronic state to be occupied, and so recurrent fluorescence. So this is why recurrent fluorescence is interesting in this kind of species. So I turn now to the results. So we have here the normalized C60 emission intensity induced by irradiation from a 20,000 Kelvin black body. On the right, we have the spectral energy distribution. And in each of these family, we have 1,000 isomers, and we took a flat population because the interstellar medium is supposed to be out of equilibrium. And for each of these emission spectra, we also have in orange the recurrent fluorescence contribution, and we can see that this contribution has always the same overall shape, which is a black body-like shape, as we shall see. And what we can say firstly is that these vibrational emission bands at around 5 micrometer are not astronomically observed. And in the first approximation, we only consider C60 cages, and we are especially interested in this near-infrared emission. The other bands are the vibrational bands. So what I want to stress here is that this emission, this continuum emission, black body-like emission, does not come from an individual carbon cluster, but is a collective emission. We can see that here. For example, we have the profile of the emission of C60 for 10 cages here, and we can see that we do not have below 5 micrometer. We have recurrent fluorescence emission, but we don't have a black body-like shape. There is no continuum structure. But if we increase the number of cages, we can see that. Please don't pay attention to this peak, to this emission. This is not an emission, actually. This is a numerical artifact. So As I increase the number of isomers, we can see that we have this emission, this black body-like emission structure gives rise. So we can see that, meaning that the black body-like emission comes from the collective emission, not from individual carbon clusters. So we have the recurrent fluorescence part here and the fit, the black body-like fit. We have here between 1 and 5 micrometer in semi-log scale, the emission of C60 kgs and C42 kgs. And in blue dots, we have the emission spectrum observed by crystal grains in 1984. So we have here the 3.3 micrometer emission supported by this plateau, this continuum emission. And crystal grain introduced the stochastic heating of very small grains to account for this near continuum emission. And our question is whether or not this continuum emission is due to recurrent fluorescence from large cage carbon clusters. So what we can say firstly is that below 1.5 micrometer, the emission, the carriers of this emission are too hot, meaning that they are small actually. So the carriers should be smaller here. The carriers should be smaller than C40 kgs, 42 kgs. But we also have some emission here, meaning that yes, we can also have some C60 carbon clusters. So very crudely, we can say that mainly cage carbon clusters should contain between 30 and 60 carbon atoms. So below 30 carbon atoms, we don't have, we have very low cages, just maybe like 20, 30, 40 carbon clusters. And above 60, the carbon cluster should be too cold to explain this black body-like emission. So we have here the black body-like emission in semi-log scale. We have the exponential. And we can go further and estimate the carbon cluster's abundance in this region. So we have some other environments here where near-infrared continuum emission have been detected, black body-like. So given that we know the relative position of the exciting star, the observed region, and the Earth, we can estimate the spectral intensity that we should detect here. So this is the spectral intensity observed at 2 micrometer by crystal grain, and this is and we can calculate it. And given that we also know hydrogen and carbon abundance in this region, we deduce that if C60 kgs are the exclusive carriers, then they should contain 1% of the interstellar carbon of this region. We did the same calculation with C42, and this percentage is 0.5. But of course, we have a size distribution, which should be between 30 and 60, meaning that the interstellar carbon, 0.5 and 1% of the interstellar carbon should be locked up in these carbon clusters, cage carbon clusters. To conclude, the main message is that the near-infrared emission in this region, Reflection Nebula, could be due to recurrent fluorescence from carbon clusters. What I want to stress is that this black body-like emission does not come from individual carbon clusters, but is a collective emission. What I didn't mention is that recurrent fluorescence has an influence on the vibrational band ratios, and that recurrent fluorescence from carbon clusters cannot account for the extended red emission, as it has been suggested since 10 years now. And in the future, we would like to extend our work to the recurrent fluorescence from large pH species and investigate the correlation with aromatic infrared bands. So thank you to my colleagues, Pascal Parnick, Cyril Falvo, Aude Simon, Mathias Rapacioli, and Florent Calvo for providing me the carbon clusters. Also Emmanuel Dartois and Yann Camille for astrophysical discussions, and my PhD supervisor, Thomas Pinot. Thank you.